Yeah, okay, welcome back. I'm assistant professor at 중앙 University. So today I'm going to talk about the mechanical property of the material. So until now, we just understand some fundamental of the solid structure system. So, but however, we do not discuss about the detailed property except some diffusivity. But in this chapter, we are going to discuss about some macroscopic property, such as mechanical or Young's modulus. I think that you guys already know that. So mechanical property is a key characteristics of some solid material. It is because that the when we design something, we usually use some solid matter. So until now, we learned about some atomic interaction and then some crystal structures or some amorphous structure. So from their crystallinity, so the mechanical properties strongly relate to those kind of some crystal or atomic orders. So so to discuss about the mechanical property more detail, we learned about some concept to describe the mechanical strength in the quantitative value. So let's keep going. So in here, first we are going to learn about some stress and strain concept. So what is the stress? I think that you guys know that stress. It is because that stress is well used as expressed your feeling or some your environment, life environment. So, but however in here, so stress is means that due to some mechanical forces, the and then strain is another terms of the some mechanical deformations. So to describe the non-dimensional cases, so that stress and strain can be used to instead of the load and displacement. And then we are going to learn about the elastic behavior. Elastic behavior means that when we apply some load to the solid structure, and then they will deform. But when we removed the that load, and then solid matter will be return their initial geometry. At that time, we call it that this solid structure shows elastic behavior. So, but however, that solid structure cannot be recovered their initial geometry after due to the loading. At that time, that this solid material experienced plastic deformations. So that compared to the elastic structure, the plastic deformation means that the solid matter permanently damaged. So in here, why the solid matter can experience those kind of permanent deformation. And then there are many a lot of the another expression, for example, that the toughness and ductilinity, those kind of terms will can define or can define some material strengths or some material characteristics, various material characteristics. So in this chapter, we are going to cover those kind of concepts. But please remind that those kind of the mechanical characteristics result from the atomic bindingness or some atomic orderness. But however, the in the mechanical engineering point of view, that atomic structure behavior, it is it is too difficult to check the full detailed atomic structure for the solid matter. But however, that those kind of stress and strain behavior concepts or some elastic and plastic deformation, you guys can easily see or check the in your life or some mechanical parts or system. So that I think that most important chapter is chapter 8 to understanding the solid mechanics. But however, that the first part chapter or second chapter is also the important. Yeah, okay. Let's discuss about some elastic deformation first. I told you that elastic deformation is when we apply the loading, the all solid structure can show us some elastic deformation. First, yeah, when we apply the small load, that the solid material can be increased. At that time, in the atomic scale point of view, the atomic bonding can be stretched. So that is obvious. So, uh, but please remind that those kind of bonding can be when bond increased. At that time, the energy can be unstable. In the from Reynolds-Jones or LJ Reynolds-Jones potential curve, so that the their energy state go to this direction from initial configuration, and then when you remove that loading at that time, this solid structure actually bond distance want to go back to their ground minimum point, so that in other words they return to their initial configurations or geometries. At that time, that the solid matter, the behavior reversible, and then we call it elastic. So that, but there are many the non-linear elastic material. So then, among the various different non-linear elastic material, one thing is plastic. So that maybe you are interested in some solid mechanics. At that time, you guys can learn about the various different types of inelastic behavior characteristics for the solid material. Yeah. First, inelastic behavior is plastic. The plastic deformation, similarly, when you applied some loading at that time, that this bond can be increased due to that load. But you apply too much forces to this solid structure, so that they will experience some too large bond movement to looks like this. At that time, that they will move to this atom from this side to this side. So at that time, that this bond will overcome some large energy activation barrier. It is because that, please remind us, some dislocation or some hardening, carbon hardening. At that time, we say that when ordered atom can move to another site, at that time they must overcome that energy barrier. To increase those kind of energy barrier, we put some small atom in ion, small atom carbon in the ion system. So that similarly, so they will some overcome those kinds of activation energy barrier due to this large forces. But however, when you remove this large forces, so at that time that atom cannot go to their initial position. So that means that their atomic position is permanently changed. So we say that that's the plastic deformation. That's the concepts of the plastic deformation actually. So that those kind of plastic deformation will be when usually occurs those kind of slip movement. It looks like some dislocation line or point and some edge surfaces dislocation. So that dislocation is one of the actually the most of the origin of the plastic deformation. So due to those kind of some dislocation, first in the initial stages, they will all solid material experience the elastic deformation. But however, when we exceed some forces or actually the stresses, at that time that the atomic or solid matter will experience the too much large deformation. for example, that dislocation at that time that they will, due to the some those kind of behavior, their forces change the some inelastic non-linear behavior due to the some dislocation that when they cannot recover their initial configuration, we say that that displacement is a plastic displacement. So that's very simple. So to discuss about the mechanical quantity, so we are going to change the forces to the stress and displacement of the solid. We are to the strain. So that to discuss about the detail about some stress, we should define what is the stress. Actually, the stress is some non uniform forces unit. Uniform forces means that the stress is another some definition of the non-dimensional not actually non-dimensional, some uniform load. Why we need those kind of some unit of the forces? It is because that when you apply some forces to some solid material, at that time that this solid structure will feel your forces. But however, if they have a very large size solid, at that time they feel some very small forces compared to the very small size solid material. So it is because so that due to that reason, we want to say that some unit area per some loading forces per unit area. So that's the very simple concepts of the stress. So that stress, so that we when we apply some forces at that time, the stress can be defined by some divided by the cross-section area. So that if they have a very large cross-section area, so in other words, they have a very large solid material, at that time that their stresses can be very small. It is because that these forces can be distributed to the very large surfaces. So this solid material can show a very large resistance. However, when you change that force's direction to this cross-section area, in other words, this shear direction, or tangential direction to the surfaces, at that time that we say that these forces can act as shear forces. So when you divide it by these forces to the cross-section area, at that time that this stress can be say that the shear stresses. So tensile stress is normal direction of the cross-section area. Shear stresses is a tangential direction to the some cross-section area. But however, so this definition, this stress definition can be defined on the surfaces. So when you define some surfaces to, for example, to the side surfaces to here, at that time these forces can be act as shear stresses, but this shear direction forces can be changed the tensile stress to these surfaces, so that the stress definition is only defined based on the cross section. So that define some area is very important to understand the stresses. So that so due to some reason that, so go to the next. So that the common state of the stress. So those kind of some tensile stresses can be detected various field. For example, that some cable. Let's discuss about some stress effect to this cable. This cable, we are going to pull this cable to move to some lift. So that at that time that pull means that we applied forces to the some normal direction, outside direction to this cable. At that time that that cable can be expressed the tensile stress. To define the tensile stress, so we should also define the cross-section area. At that time, that exact stress value can be obtained from the forces divided by the cross-section area. So that's the simple tension cable cases. But sometimes that we can some solid matter can be exist in the torsion state. Torsion state means that we rotated some solid material and looks like this. So that this is a moment like behavior. So that at that time that this is some cross-section surfaces. So when you check the some unit solid volume element, at that time this cross-section area they will show those kind of shear movement, so that this act like shear forces, so that this solid metal can exist in the shear stress state. The shear stresses can be defined by the shear forces divided by the cross-section area. So that's the good example of the tension stresses and shear stresses in the cable state system, cable-like state system. So in here, to pull in this cable, this part must be rotated. This shaft is exists in the torsion or rotation movement. To give a rotation movement to this lower part, at that time we should apply very large torque or some moment to here. So at that time that this solid shift can be can experience the torsion behavior. So there are another some good more example. So let's see that this rock experience gravity. So due to the large amount of the masses, so their gravity forces can be large. So that, but however, this part they can sustain this very large weight of the rock, and then but if they have a very small cross sections to here, at that time this rock can be broken. But however, they have enough large area so that they can sustain those kind of forces, exactly stresses. So that this part is under the compression stresses, simple compression stresses. If you due to some reason that their cross section area can be reduced to looks like some wind or some other things, so that at that time that they cannot sustain this compression stress anymore, at that time this rock can be rolled down. And then let's see the 계속 이어서 sorry for the some noise. So let's see this bridges. This bridges is under the compression stresses. It is because that they have a very large weight of the plate. This plate also experiences gravity forces. But however, without this bridges, so I'm not sure how can I say it, but so they can sustain this traction, so that this actually the beam structure is under the compression stresses. So for the stability, mechanical stability of the bridge, so that we should check their stress state due to some gravity or some if some car is on this position at that time, that the gravity forces or actually the forces can be increased at that time. This compression stresses can be slightly increased. So another example is a biaxial tension cases. So that when we think about some hydrogen tank or gas tanks, so we put a lot of gases to inside this tank. At that time, their pressure can be increased. So due to this gas pressure, they will expand. They tend to be expanded more. So at that time these cases cannot move to this direction. So but in other words, so they must show some resistance to this pressure effect, so that these forces can be shows some uniform distraction. So this or some time that okay, let's change some images, so that put some that direction. So at that time that due to some reason, this cross-section surfaces area can be tended to be increased. That means that the stresses can be exist the whole plane whole direction, so that we say that this is a biaxial tension stresses. If we have only one single direction tension stresses, at the time that we say the simple tension state. But however, if they experience the two different direction, at the time we say that the biaxial tension. Yeah, hydraulic static pressure is triple axis tension or compression stresses. So that most cases the pressure hydraulic static is we say that the compression status, so that we usually say the more compression than the tensile tension cases. So that when you are inside in this gas tank or some water, at that time that you feel the uniform pressures. So at that time that we say that the hydraulic under the hydraulic static pressures. So that we discuss more. We discussed the stresses, concepts of the stresses. Let's go to the next strain. Yeah, strain is some definition of the non-dimensional material length changes. So if they have a solid matter has a unit initial length L0, due to some forces, that solid can be deformed. We say that this solid will deform the delta, amount of the delta. At that time that we can say that the changes of the solid material is delta L0 over the delta, or another things is L0, the deformed length is L, and then divided subtracted to the L0. So that this is a concept of the strain. So that their unit is a meter, and then some also changing is a meter. So that the strain is a non-dimensional unit. So that lateral strain is means that some when they deformed some deformation at that time due to the volume conservation, some lateral direction must be shrink. So that at that time that we can also check those kind of lateral solid material changes. At that time that the initial lateral width is W0, and then after the deformed W and the initial W0 subtracted, the total change is delta L. But at that time that the changes is minus. So that however anyway we can define some lateral strain. Yeah, that's the obvious behavior. So and then another strain is shear strain. So we discuss about the shear stresses. The shear stresses forces act to the normal direction, tangential direction of some surfaces. These surfaces. At that time, that we should also define that that's shear stresses. So that shear stresses is defined by cross-section area of the shear forces. But similarly, we also can define the changing of the displacement. But however, that their initial their length does not change. But however, one thing changing is angle. So the shear strain is we can define the angle-like behavior. But initial direction, initial length is y, but the length changes to delta x. But that changes is differ to the y lengths. So that please remember that due to the reason that the initial length is y and the changing of the length is delta x, but they are perpendicular each other. So that, but due to the reason that the almost solids will deform very small, so that the due to some assumption we can say that tangential this is equal to the tangential theta, but it's almost similar to tangent theta. So that always the strain is non-dimensional and then very small things. To check those kind of stresses and strain, so we have some utility. Yeah, for example, typical tensile test machine, or sometimes the universal tensile machines. So that after attached to some load cell, this load cell looks like your weight machine, measuring the weight machines. So that, and then after put the some species, solid specimen, and then we attached some strain gauges. We sometimes call it the extensometer. This extensometer, so when we applied some loading to here, so they will rotate it. This screw will increase will change this direction. This solid metal will be experience some tensile forces, and then this some tips can be detected some changes of the solid deformation. So from here, so we know that the initial length of the specimen, and then we can know that the changing of the length is from the extensometer. So from here we can detect the some strain, and then we can detect the forces. But to convert these forces to stress, so that you should also know that the cross-section area of the specimen and looks like this. So that the conventional some tensile test machines. So that to check the material characteristics, although that they will experience elastic deformation or plastic deformation, so that but if they are strongly affected by their geometry, so that there are some standard geometry of for the specimen, so that usually they have some large radiuses, and then the species center part will has a small diameter than this outer part. So that but ASME or some I forgot the American standard some blah blah blah. So they will define the standard specimen for the those kind of tensile tests. Yeah, so that to check the some stress strain of the material, solid material, there are some many things. Extensometer first is extensometer. So second case is strain gauges. Yeah, this extensometer it can be used several times, so they detected some matter. But however, that the one thing problem is when we apply the very large forces, so this solid metal will deform too much at that time that this detected part can be also damaged. So that usually we also usually use strain gauges. This strain gauges shapes and looks like this, and looks like some they connected some electrical wire. So due to the some deformation, these lengths can be changed. In other words, means that when we applied some current to here, there due to some resistance in the solid metal, their voltage drop can be detected. But this length is increased, means that this R resistance also can be increased. That means that voltage changes is slightly changed. From there, we can check the how much solid material will increase or decrease. That's the strain gauges. But the one thing problem, this wire part very weak, so that after one time you used, and then we cannot use it anymore. So you should replace the strain gauges ever tested. That's the problem to obtain the exact strain. to overcome those kind of problem, so the researcher developed non-attachable, non-attachable or some cases, some measurement techniques. That's the we say the digital image correlation method. This digital correlation image method, that's very simple cases, simple. So when we put some mark to the solid species material and looks like black dot. So and then when you pull out this solid species, and then you can track this black dot, how much they will move to. So that from that contour plot is that solid that black dot moved, how much moved to here. So that when you have some just camera with a high resolution camera, and then this solid structure has some dot can be detectable using that camera. At that time, that you can easily detect those kind of strain field. So that the advantages of using the digital image correlation method, we do not need to those kind of attachment or strain gauges, extensions or mirror. But the disadvantages is without those kind of geometric graphical mark, they cannot determine the exact deformations. But these days, the non-detachable, non-attachable the measurement technique, digital image correlation method is well known to here. Yeah, so that I so prepare the digital image correlation method. So for example, that the conventional universal tensile machine, so that when we attached some specimen and then applied some load, and then so that we can also attach some strain gauges. But using the camera, you guys can detect some pattern, and then during the elongation, we can track this pattern can be how much patterns are changed. So that using those kind of the grid tracking methods, and then that grid can be to match this grid. So the from those kind of technique we can obtain those kind of strain field easily. But the one thing problem, so that to obtain those kind of strain field, so that tracking of the particle image particle processes need to the several snapshot to change into this part, go to this part. So that without the very accurate images at that time, we cannot achieve those kind of goals. But however, those kind of digital image correlation method can be used various different types of the solid specimen. Actually, the universal tensile machine has some limitation to obtain some stress and strain property. It is because that they have some standard shapes to obtain the exactly. But however, those kind of digital image correlation technique can be used various different types of the shapes. So that in other words, that when we attach some solid material to some system, at that time you can also directly check the strain field. For example, that those kind of crack edges here, or some already attached by the screw or some pipeline impact, so or things. So and then these days, due to the development of the camera techniques, so that we can also check the three-dimensional displacement field looks like this. So I think that there are many things, but I think that the current state of art, the measurement of the strain is a digital image correlations, I think. The one thing we can point without the pattern, yeah, we cannot measure. So that, but to generate the pattern is the easiest way is putting something, for example, that spray So that those kind of things we can make the artificial pattern for the solid material. Yeah, so we learned about the stress and strain. And then from this relationship, we can define some material property. First material property is Young's modulus, yeah, or modulus of the elasticity. Yeah, from the stress and strain relationship in the elastic behavior shows a linear behavior. So from here, the slope can be, we can define the Young's modulus, and then this relationship, the stress and strain relationship has a linear relationship, means that we need some one coefficient is that's the Young's modulus. That relationship we say that the Hooke's law. That's the basics of the solid mechanical behavior. And then next material property is Poisson ratio. From until previous slide, when we applied some solid matter, this solid will increase, looks like this, but this lateral direction, that they will shrink due to some volume conservations. So that relationship, this to the strain, that's also strain, but the elongation, longitudinal, and this is a lateral. And then that ratio is a Poisson ratio. Always the tensile direction is positive, but sometimes negative is under the compression stresses. But the lateral changes is opposite, so that we put some the negative sign to here. So that the depending on the material, so that their Poisson ratio, the ratio is slightly different. So that from the here we can easily define the sometime that when the Poisson ratio is 0.1/3 at that time metal, but the 1/4 at that time that ceramic material. But polymer material is shows a 0.4 value. That is almost similar to the 0.5. This 0.5 means that the perfectly volume conserved behavior. So that maybe the rubber material is almost the shows a volume conserved deformation. Their Poisson ratio is 0.5. But the polymer, so in other polymer is almost similar to the rubber material, so that their Poisson ratio is extremely similar. But the other material, they do not show a volume conserved deformation, and this is they shows a brittle behavior. So that the 0.5 means that they are volume conserved, but when their density is different, at the time density is slightly decreased due to the all solid material has some void. So that this void is slightly reduced, so that their density is slightly increased. But I never seen the over the 0.5 for Poisson ratio material. So, but sometime that the one thing interesting is some negative Poisson ratio. Yeah, let's see those kind of some complex geometry. So when they pull out, at that time their lateral direction is increased. This the opposite behavior, which we already know that. So that means that when you increase the longitudinal direction, this part also can be lateral direction also increased. That time, we defined the Poisson ratio has a negative sign, but both are positive. So total value is negative. So we call it a negative Poisson ratio. Those kind of negative Poisson behavior is very special characteristics, so that we want to know that the detail. So, but you guys, although that you are not familiar with those kind of behavior, but you already know have some those kind of shoots. In here, you guys can see the very complex geometry in the bottom of the shoes. Yeah, for example, that the shoes when you work or running, the shapes can be and looks like this. This is a ground, and the part this looks like this. But that means that they will experience those kind of longitudinal direction. But the conventional material can be experienced those kind of some positive Poisson behavior. That means that this part is shrink. That means that your shoes will be pressed your foot, so that they will be hurt. But however, if when they show a negative Poisson behavior to this direction, at that time that your foot will feel comfortable. So that due to the reason that the negative Poisson ratio can be used to those kind of applications. So that due to the scientific importance, so that many guys reported those kind of complex behavior, including negative Poisson ratio, so that the science is top journal in the scientific or engineering field, so that they also reported those kind of the solid material behavior. So that in the nature's material, I also introduced something, so that those kind of things is electronics, bioelectronics chips or pattern to detect some signal from your brain or heart. So that, but however, one thing problem, so that our body, inside body has a very complex curvatures. Due to those kind of reason that we cannot perfectly attach those kind of flexible devices to our inside body. So that to overcome those kind of problem, we use those kind of axonetic material or very complex material. So the key concept is they will differently shows some mechanical behavior, exactly negative Poisson material. So these days that also that one important thing is some twisting material in the science. Also that they will some report is some material is reported. So three-dimensional mechanical meta material with a twist. So in here, from there, so they will mention about some special behavior. For example, that when we applied some torsion behavior, at that time the effective or some things is slightly different, but however they will show a very extremely high the twisting resistance, although we do not use a large enough material, so that so they have a large enough void spaces, so that due to I'm not sure that how they find it, but however their mechanical behavior is almost similar. That means that although we use the very small amount of the material, but we obtain the very high strengths or actually the high twisting resistance material using the material. So those kind of material can be used the various fields. So I think that you guys can be interested in those kind of things material. So that first lecture I'm going to stop to here. So let's continue the mechanical property in the next lectures.